The equation y is equal to minus x squared plus 16 intersects the x-axis, and the horizontal line with y equals 7 as the equation at m and n. Determine the coordinates of a and b. If y is equal to minus x squared plus 16, a and b were basically where it crosses the x-axis, so that means that y is 0. So set y equal to 0, and when you do, you get 0 is equal to minus x squared plus 16. Bring the x squared over, so that means x is equal to plus or minus 4. So this is obviously, the a would be minus 4, 0, and the b would be 4, 0. Determine the area of trapezoid MNBA. So that trapezoid, let's just draw it here. It's kind of like this, right? So A, B, and M and N. Now A to B, that's 8, since we're going from minus 4 to 4. And then the top to bottom, that one, that's going to be 7, because it's going from the line, the x-axis, to this line, which is y equals 7, as given in the question. And then M to N, that I would have to do a separate calculation. That is when y is 7, we have to figure out what is x. So that's going to be x squared is 9, so x will be plus or minus 3. So that's going to be, m is basically minus 3 and minus 3, 7, and n is 3, 7. So to go from n to n, it's actually 6 in terms of the length. So the area of a trapezoid, you'd go 6 plus 8 divided by 2 times that height. And that, I believe, when you do that math, is 49. Suppose that O is the origin and that V is the vertex of the parabola. The line y equals negative 33 intersects the parabola at P and Q. Determine the area of quadrilateral VPOQ, which is the shaded in the diagram. Okay, very similar. VPOQ, I believe, would be VPQ minus OPQ. And that's going to be 1/2 base times height minus 1/2 base times height. So let's figure out what those are. OPQ, okay, this is y equals minus 33. Yeah. Was that the line? Yeah, y equals minus 33. So y equals minus 33. So that means that the height, this top to bottom right there, is 33. Because it's got to be a positive number, right? And then to get from V to Q, we have to do that calculation. So minus 33 would be minus x squared plus 16. So that means x squared is 49. So x is plus or minus 7. So you're going basically from a minus 7 to a 7. So that's 14 in terms of the length. Okay, now we'll turn our attention to VPQ, the big guy. I think the base is the same. So that's 14. But the height is going to be all the way up to V. And what was that? That's the y-intercept. So that would basically be when x is 0. So minus, when x is 0, y is 16. So that's 16 up there. Yeah, this guy. So that means that the top to bottom would be 16 plus 33, so that's 49. So there you go. So this looks like 7 times 49 minus 7 times 33. So factor out the 7, you get 49 minus 33. And that's 16, so 7 times 16, which I believe is 112. Determine all real numbers a greater than 0 for which a squared plus a under the root is 2/3. Let's square both sides, and when we do, we get, what is it, 4 over 9. And then bring it all to one side. A squared plus a minus 4 over 9 is equal to 0. And then I can factor this. I don't need to do a quadratic. Let's see here, 1/3 and 4/3. That would give me 4 over 9. And then the symbols minus plus, I think. Yeah, minus plus would do it. So that means a is equal to 1 over third or negative 4 over 3, but they told me that a is greater than 0, so therefore a has to be the 1/3. For each positive integer m, determine the difference between m plus 1/2 squared plus m plus 1/2 and the nearest perfect square. So for example, if I asked you the difference between 7 and 12, well, you just go 12 minus 7, and that's 5. So they're asking you the difference between this and the nearest perfect square. Okay, what is that? Well, let me I'm not sure. Let me expand that first. M squared plus m plus 1/4 plus m plus 1/2. So that's m squared plus 2m plus 3 over 4. So that's obviously greater. Let me think about this. That's obviously greater than m squared, because m is a positive integer, so this obviously would make it greater. And then let's see, how does it compare to m plus 1 squared? M plus 1 is m squared plus 2m plus 1. So m squared plus 2m, it would be less than that, because this is less than 1. Okay, so it's immediately in between, but we have to find the nearest. Is this the nearest, or is this the nearest? Well, well, the difference between this whole thing and this whole thing is the difference between that and that, so that's 1/4, right? 1 minus 3 over 4 is 1/4. And the difference between this and this is 2m plus 3 over 4. And since m is a positive integer, the smallest it could be is 1. So that'd be a lot. That'd be a lot more. That'd be 2 3/4. So I guess it's closest to this guy. Let me just think about that for a second. Yeah. So what we're asking for is the difference between that and the nearest perfect square, which I'm concluding is m plus 1 squared. So just like how I did that difference, the difference that we need to do would be m plus 1 squared minus that m plus 1/2, all that stuff, plus m plus 1/2. Okay, so this is m squared plus 2m plus 1, and then this guy, we already expanded that upstairs, so 2m plus 3 over 4. And then when you do that math, everything cancels and you just get 1/4. Yeah, that's it. So that's the answer. For every positive integer n, prove that the number of positive integers c with n less than the square root of c plus square root of c is less than n plus 1 is even. What are they asking here? Let me give an example. Let's say n is equal to 5, and therefore that equation would become 5 is less than the square root of c plus root c less than 5 plus 1, which is 6. If we square both sides, it would be c plus root c, and this would be 36 and 25 on opposite ends. So they're saying, for what values of c is this going to be true? And remember, n is a positive integer, and c is a positive integer. So, you can kind of go through this, and you'll find that c can be 21, 22, 23, 24, 25, 26, 27, 28, 29, and 30. So how many c's do we get? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we got 10 values. And 10 is even. So since 10 is even, we have proven, just for n equals 5, that the number of c's is even. Got it? So that's basically what they're saying. But they're saying prove this for all n, not just for 5. Okay, so how do we do that? Well, I think the simplest way is just through a system of extrapolation. And let me explain. So we just do it for n equals 1, n equals 2, n equals 3, And let's see if we get some sort of a pattern. I actually already did it for n equals 5. So then you can do it for n equals 4. You know, n equals 5 we already did. For C we got 10 values that we just did. So like right here, right? So let's do it for n equals 1 and n equals 2, and let's see what we get. And let's see if we can come up with some sort of a pattern. Okay, if n equals 1, then that equation becomes c plus root c 2. And then if you square both sides, it becomes c plus root c 4. Is that right? No, sorry. That should be 1. When you square 1, you get 1. You don't get 2. Okay, so this equation, or inequality, rather, you can just do it by inspection, right? I wouldn't square both sides and all that stuff. Again, by inspection, you'll get that c can be either 1 or 2. So how many values of c did I get? I got 2 values. So I got 2 values when n equals 1. Okay, I got 10 values when n equals 5. Okay, let's keep going. When n equals 2, that's going to make the equation 2 is less than c plus root c, less than 3. If I square both sides, I get 4, less than c plus root c, and that's 9. And then again, by inspection, you'll get that c is equal to either 3, 4, 5, or 6. So that gives you 4 values. So n is 2, we got 4 values. Let's try n is 3. And then I'll let you do this. You do this then, because I'm sure that you can. N equals 3, we'll get 3 less than root c plus c less than 4. If you square both sides, you get 9. C plus root c is 16. And by inspection again, you'll get c is equal to 7, 8, 9, 10, 11, 12, and that's 6 values. So when n is 3, you get 6 values. So in general, it seems that for n, the number of values for c is 2n. Right? When it's 1, it's 2. When it's 2, it's 4. When it's 3, it's 6. When it's 5, I showed it was 10. And you're going to do what it is for n equals 4. And 2n is obviously an even. All numbers of the form 2n are going to be even. So there you go. For each positive integer n, let s at n be the set of that contains the integers from 1 to n inclusive. That is, s at n is 1, 2, 3, ... until n. For each positive integer n greater than or equal to 4, let f at n be the number of quadruples a, b, c, d of distinct integers from s at n, for which a minus b is equal to c minus d. For example, f at 4 is 8 because the possibilities for a, b, and c are as follows. So to determine the value of f at 6. So let's understand this question first. F at 4 is 8. So what did they first do? First, they figured out what is s at n. And s at n would be 1, 2, 3, 4. Basically, or actually what I really wrote is s at 4, where n is equal to 4. And that's entirely based on that definition. And then what they're saying is choose any 4 of these. Choose any 4. Well, there's only 4, so we can only choose those 4. And then choose them in pairs so that a minus b is equal to c minus d. So if you were to choose a pair of that nature, a, b, c, d, a minus b is equal to c minus d. Well, one such example would be if I chose a and b to be 1 and 2, and c and d to be 5 and 6. Therefore, a minus b would be 1 minus 2, which is negative 1, and c minus d would be 5 minus 6, which is also negative 1, and therefore that matches. So that quadruple would be 1, 2, 5. Oh, sorry, what am I doing? I jumped ahead there. Sorry about that. I jumped ahead. Should have been 3, 4. I got to concentrate on this. I'm thinking about this already. Sorry. So, well, in any case, it's the same thing. It'd be negative 1. So it'd be 1, 2, 3, 4. Not very exciting, but that is one of the quadruples, and they list that in there. But you can also get the same thing if you did this or this and so on. So that's why there's so many of them. There's 8 of them. And therefore f at 4 is 8, because that's the 8 represents how many quadruples you can get by doing that. So now they're saying determine f at 6. So f at 6 is a little bit different. F at 6, first you have to figure out s at 6. That's 1, 2, 3, 4, 5, 6. So that's where that 5 and 6 came in. That's why I was excited to do it over there, even though I'm explaining this guy. Okay, then first thing we need to do is choose 4. Choose 4 of these numbers. So let me choose the 1, the 2, the 5, and the 6. And I've chosen those specifically. Why? Because I have to abide by that rule. So if this is my A, B, this is my C, and D, this rule has to be fulfilled. So A minus B in this case would be 1 minus 2, which is negative 1. And C minus D in this case would be 5 minus 6, which is also negative 1. So that holds true. So this is indeed a quadruple. That quadruple. That satisfies the conditions. So we have to figure out how many of those. Okay. Well, there's going to be quite a few. But before I get into how many, one thing is for sure is that this guy, that just those 4 numbers can be made into other quadruples that satisfy our condition, which was this guy right here. So let me just write down what this guy satisfies in terms of its iterations or arrangements. So the first one is the original one, but 5, 6, 1, 2, that also would work. And then so would 2, 1, 6, 5. And these are not that difficult to figure out. 6, 5, 2, 1, that would also work. 1, 5, 2, 6. 2, 6, 1, 5. 5, 1, 6, 2. And finally, 6, 2, 5, 1. So as you can see, for each original that I created, I can make 8, I guess, arrangements. Yeah. So, I guess what we'll do with that is figure out how many originals I can make. I made 1 original there, and then multiply the originals by 8. So, let's see what happens if I do that. So, this is the first one. And let me insert a graphic here. So this is a very important graphic that shows all the possibilities. So I did the first one when we have A and B equal to 1 and 2. And then I chose this guy, 5 and 6, to kind of give my example. But as you can see, there's many other possibilities. If you have A and B as 1, 2, you could also choose C and D to be 3, 4, or 5, 6. 4, 5, or 5, 6. If you chose A and B to be 2, 3, C and D could be 4 or 5 or 5 or 6. So if you add up these, be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So you'd have 14 original quadruples. And then each of them has 8 arrangements as shown here. So each has 8 arrangements. So therefore the total would be 14 times 8, which is 112. But however, that 112 double counts. So you'd have to divide that 112 by 2 and getting a final answer of 56. Now, why does it double count? And I think I need to show that. For example, let's say you had just let's just choose R1. We had a 1, 2, this guy, 1, 2 with 5, 6, the original one, 1, 2 with 5, 6. We got these guys, these 8, right? Well, we got the original, which is 1, 2, 5, 6 up here, and then we made those 8 arrangements. But interestingly, you'll notice that if you chose 1, 5, this guy down here, with 2, 6, which is the only one that's listed, you would get the same 8 arrangements. And try it and you'll see you get 1526, and 1526 is already there, and then all the other arrangements would be the same. So you'd get double. So because you get double, you have to take that 112 and divide by 2, and when you do, you get 56.